Okay.
Yes. Okay. All right. I guess we can start now as well. Is that okay?
Yes, yes, please.
Okay, great. So it's a pleasure to have Hiromu Tanaka from Tokyo with us tonight. Well, tonight for us. Um, he is going to talk about Mori fiber space and positive characteristic.
Thank you for introduction and the invitation. So, as in the title, today I'll talk about Mori fiber spaces in positive characteristic. So we work over field, and we are mainly interested in algebraic closed field, and the characteristic is positive. And the motivating conjecture is MMP conjecture, which states that any algebraic is birational to either a minimum model or Mori fiber space. And the topic is Mori fiber space. So I would like to start with recovering the definition of Mori fiber spaces. So before defining the Mori fiber space, I would like to give a definition of KLT singularities. So the definition, so let X be a normal variety. And in this talk, variety means an integral separated scheme, which is of finite type over the field K. So I think this is the usual definition. Then we say that X is KLT. So this is usually said to be the pair. X0 is KLT. And its definition is as follows. So I wrote two conditions. First, we assume that some multiple of Kx is Cartier. This is called Kx is Q Cartier. The second condition is we take a projective birational morphism from a normal variety. Then we can define E, which is G exceptional Q divisor, which is uniquely defined from G. Then we assume that this is the quotient of E is larger than -1. This is a definition of KLT. So this is random fact, but so I should mention that if X is smooth, then it is KLT. Next, I would like to give it the definition of Mori fiber space. So the definition of Mori fiber space, let X be a KLT variety. So by definition, we assume that this is normal variety. And we say that the morphism from X to B is a Mori fiber space if the following four conditions hold. First, we assume that the morphism pi is a projective morphism of normal varieties, and it satisfies this condition. Push forward of structure sheaf is structure sheaf. The second condition is minus k is anti-ample. Sorry, minus k is ample, relatively ample, and the dimension strictly drops, and the relative Picard number is equal to 1. Now I want to add a few remarks. First, we are at a case when the dimension of the base is equal to 0. And in this case, minus kx is ample by the second condition here. And we also have the Picard number of x is equal to 1, which is nothing but the first condition. So Mori fiber space is, if we believe the MMP conjecture, the Mori fiber space is one of the end product. So it is important to establish many properties for Mori fiber spaces. So first, I would like to summarize such properties in characteristic 0. So now I assume that the characteristic is equal to 0. And we take a KRT variety and modify the space from X to B. Then as a first property A, the general fiber is KRT and it is Fano. So this holds by Bertin theorem. As a second property, we have that the higher direct image of the structure shift vanishes. This is a consequence of count-Friedrich vanishing theorem. As a third property, if L is a calculated by the on X, which is relatively numerically trivial, then it is actually trivial. Now I would like to give the definition of this one. So maybe many people might know this. So numerical trivial means that the intersection number with C is 0 if C is a curve on X, which is contracted by pi. So which I mean that C is a curve on X whose image by pi is a point. The latter one, the relatively linear trivial means that L is a pullback of the line bundle from downstairs, B. So, and I want to show you one more property. So the property A is about fibers, and the first property D is about the base. So if X is Q factorial, then the base is KRT. So Q factorial is a mild condition. So, and in many cases, so in many definition of morphic spaces, we actually assume that X is Q factorial. So this is a very mild condition. So these four properties are what I want to show you. And now I want to switch the situation in positive characteristic. So the first question we want to consider is the same property holds in positive characteristics. So I mean, I showed you the four properties. So it is quite natural to ask whether this property also holds in positive characteristic. So the first question is A. So so we have KT variety in positive characteristic and we have more fiber space. Then general fiber is KT or not? Then the answer is no. Then next, the second property, the vanishing of higher cohomology. So the answer is again no. And let's go to the third question. If we have a relatively numerical trivial line bundle, then it is actually trivial or not. So the answer is again no. For the last property, so if X is Q factorial, then with KT or not? The answer is again no. So all the property does not hold in positive characteristic. So now I would like to show you some examples, counterexamples, and some details on these answers. So from now on, I assume that the base field is of positive characteristic. Okay, the first question was if we take a Mori fiber space, then the general fiber is KT or not. As I said, the answer is no. Here is an example. So for simplicity, let me assume that the base field is a closed field and assume that the characteristic is equal to 2. So the base of the Mori fiber space is the three-dimensional affine spaces, and X, the total space, is a hypersurface inside this direct product, P2 times H3. The equation is as follows: T0 x0 squared plus something like this. Then T is a parameter of this one, and X is a parameter here. Then it is easy to see that this is Mori fiber space. For example, this is X is smooth fourfold. This can be checked by the Jacobian criterion. And in the question A, we ask whether the general fiber is KT or not. But in this example, any geometric fiber is not reduced. So in particular, this is not normal. So it is not KT. So this is because, so we take, for example, a cross point and its fiber. So A0 and A1 and A2 is an element of K. Then the fiber is a curve inside P2. The Xi is still a variable, and the Ti is replaced by Ai. So the equation becomes A0 x squared plus something like this. Then in characteristic 2, this is not reduced because this can be written as like this. So any fiber over cross point is not reduced. And it is easy to generalize this example to any positive characteristic. So this example can be generalized to any characteristic P. So the example becomes like this. So B was A3 in the case when P is equal to 2. For the general P, we take B to be the P plus one dimensional affine spaces, and X is hypersurface like this. T is 2 is replaced by P. Next, I would try to go to the question B. So it asks whether given a Mori fiber space, then the higher direct image of structure shift vanishes or not. As I said, there is counter example. So this is a example. There are less information. So the example found in the case when P is equal to 2 or 3. So we take a algebraic field whose characteristic is 2 or 3. Then we can find creative priority and Mori fiber space and its the higher direct image of structure shift is not punished. So the first such example is found by Schwer in 2007, and Madokiba-san also some other constructions, and in this case gives the example in characteristic 2, and my example is characteristic 2 and 3. And before going to the details, I would like to mention open problems related to this question. So, as written here, the characteristic is 2 or 3, but this is only characteristic who has counterexample. So we do not know whether counterexample exists in the other characteristic. I'm pretty sure they exist, but now it is not known. Another question. So since we have such example for modifiable spaces, so it is natural to have it is natural to expect an example for mild conditions. I mean, for example, one of extreme case is smooth fan varieties. So also for this case, similar counterexamples should exist. So what do I mean? The question is for smooth fan varieties, then the direct image of the structure shift is punished or not. This is open. And as I said, I think that there exists counterexample, but we do not know. And this implication actually holds if the dimension is at most 3. The 3-dimensional case is proved by Schwarz-Baron and Kawakami. Now I want to add some details on the construction of this one. So I give you the details on my example. The strategy consists of 2 steps. The first step is to construct something, some pathological example of impact field, and the second step is to spread it out over some spaces. So I will look at more details. So fix agile closed field of characteristics 2 of 3, and set F to be the this field, so rational function field of degree 1, the function field of P1. Then what we first do is to construct Kelty derived surface over this imperfect field, which is 2-dimensional and minus K example. This is usually called derived. And corresponding to the this property, we found Y with this property. After that, this implication is just a routine. So we spread Y over open subset of A1. So just killing denominator, we can find this such fiber square. Here, so spec F is the joint point of B. So Y is the joint fiber of pi. So joint fiber satisfies some bad property. So fibration should satisfy some bad property. So more precisely, we have this non-vanishing, then flat base change theorem shows that higher direct image does not vanish. Because from here to here, we get from here to here is obtained by tensor product with a function field. So this implication is okay. So the crucial part is to construct the crucial part is the first step. So which is the construction of pathological derivative surface over F. So here, I think no information might not be added, but so if it's the general statement is as follows. So we take a field whose characteristic is 2 or 3, and assume that this is not perfect, then we can find this this derivative surface. So I mean, projective characteristic surface, and minus k example, and Picard number is equal to 1, and H1 is not vanished. And also, so we have this property. So I wrote this property here because this will give the negative question to the third properties, third question C. So this one will be used and using this construction to construct a counterexample to C. So C was asking whether given more fiber space, then there exists a non-trivial numerical trivial torsion line bundle. Anyway, so what we want to do is to construct such surface Y. This can be constructed by the theorem 2 I write down now. So this implication is almost implied, but this gap is not so difficult. I do not explain the gap, but anyway. Theorem 2 is as follows. So K, F is as before, so we take an imperfect field. Then we can find a fiber space over F as follows. First, C is a regular projective curve with this property. So if the base field is algebraic closed, then C is nothing but an elliptic curve, but this is not smooth. So this is a typical phenomenon of which happens over imperfect field. And F is P1 bundle, so it's very nice vibration. So this is a usual definition of P1 bundle. So I mean, it's a projective bundle associated to the rank 2 vector bundle or C. The third property is similar to this Fano condition. So it's slightly different, but and I did not explain what is a KT for pair, but it's a very nice condition. So this condition implies this one. So this is so in a sense corresponding to this one. And corresponding to the first property in theorem 1, we have this one. The other final property, so we have that have a negative curve. And the relation between y in theorem 1 and z in theorem 2 is as follows. So first we have z as in theorem 2, then contraction of gamma is nothing but y. So from z to y is a contraction of gamma. And also we assume the non-vanishing of h1. So this follows from theorem 2 if we assume this one, because, oh, sorry. Oh, sorry. So I pressed something. Mm. Oh, sorry. So, so now I want to explain why this holds from theorem 2. So what we want to compute is h1 of y. So this is not trivial, but not so difficult. We can think that this is isomorphic to the first cohomology z. And then this is the first cohomology of C, because from Z to C is a P1 bundle. And finally, the first cohomology of C is not zero because KC is trivial. So use the third duality. That in here, this argument is the same for elliptic curves. Anyway, so what I want to explain now is the rough construction of theorem 2. So I did not give the details, but the construction can be given as follows. So now I give a construction, but without details. So the characteristic is P is equal to 2 or 3, but so both cases are the same. So I only choose the case when the characteristic is equal to 3. And I also assume that the base field is a function field of P1. In this case, it is enough to take C to be this one. So this is a cubic curve inside P2. So if this is smooth, then this is actually an elliptic curve. But as I said, this is not smooth. So this is the generic fiber of a quasi-elliptic fibration. So the best change of C to the algebraic closed field is a cuspidal cubic curve. So this is not smooth, but this is regular. So, and we fix a rational point. Any rational point is fine, but this is Weierstrass form, so it is easy to see that this is actually a rational point. Then we see that this cohomology is not zero because we see that Kc is equal to 0 because C is a cubic curve, and we take a self-duality. Then this becomes H0 and Kc plus Q, but Kc is superpunished. So this is H0, self-dual of this one. Self-dual of this one is H0 CQ. So this is not 0. So we can take a non-zero element here. Then this is non-zero element of this H1. So if we consider this one as an X group, then this corresponds to a rank 2 vector bundle. Then, as I said, that is defined as a projective bundle of projective bundle associated to the rank 2 vector bundle. And what is remaining is how to find LZ. So to find L0, we first take LC and take pullback to Z. And LC is a line bundle on C, which is defined as the difference of two distinct rational points. And so this follows from the fact that C is not isomorphic to P1, and Q1 is not equal to 2. Q1 is not equal to Q2. So to find such rational points, I take this equation. So also in characteristic 2, for the characteristic 2 case, so we take suitable equation to assure this rational point condition. Then we can find similar example. So I did not give the proof of this one, but I did not add any more details for this example. Now I want to summarize the construction. So we start with an algebraic closed field of characteristics 2 or 3. And let F be the function field of P1 over K. Then we can find Y, which is a projective characteristic surface over this imperfect field, which is del Bezzo and non-vanishing H1. As I said, this can be obtained as a contraction of Z. Z was a pure bundle. Then from this one, we spread out over this open subset. So this is a generic point of A1. So we can find open subset which defines Y. So it is denoted by X. This is nothing but what we want. Okay, then next I want to go to question C, but I almost explained about it, so I do not give the details. But let us recall what was the question. So we take characteristic variety and take a modifiable space, and for characteristic divisor on the total space X, if L is numerically trivial relatively, then it is actually trivial or not. As I said, the answer is no, and we can find such example for this one. And Y has line bundle similar to this property, then we can extend from Y to X after replacing B by a suitable affine open subset. And again, as open programs. So we do not know whether similar example exists in the other characteristic. And also for smooth form varieties, I did not. I think it is not known that this kind of property holds or not. And again, this holds up to dimension 3, proved by Chabal-Baron and Kawakami. Okay, then I go to the last question, D. The last question was asking about the base space of the monofiber space. The statement was as follows. First, we take a Q factorial KRT variety, and we take a monofiber space. Then the base is KRT or not. Then, as I said, the answer is no. So there are two types of counterexamples. The first one is characteristic is equal to 2 or 3, and the other one is characteristic is at least 5. Then the small characteristic case, the example found for this case is. And the larger characteristic case, the base space is again of 3-dimensional, and the total space is P plus 3-dimensional. So first, I would like to mention what the construction is. The construction of the first one is to use the P1 bundle ZC, which I explained before. So to get this example, so the construction is not so difficult but messy. So I'd like to explain the second example. So this is construction itself is very easy to understand, although the proof is difficult. So this uses valid quotient. So now I explain the details of this construction. So the group we use is the simplest one in a sense. So that will PZ. And we take two varieties on which G act. The first variety is the P product of P1. So the action is given by the cyclic permutation. So if alpha 1, alpha 2, alpha p, then each alpha I is an element of P1, then this goes to alpha 2, alpha 3, alpha p, and the last is alpha 1. This is the action of the generator of this one. The second one is action by the Iris representation, so which is the action by the Jordan form. This is order 3, so order P. So now we have two varieties on which G acts. Then we take a fiber space on which G equivalency acts. And for the base space, this is nothing but this one. And the total space is the direct product of this one and this one. So we take the diagonal action. So this is G equivalent action. So we can take the quotient and we have a commutative diagram. And we can take that this is a morpho space. Of course, we need to check some details, but I do not give the details here. This is x and this is v. Then what is the difficult part is to check that x is KRT and v is not KRT. But this is assured by Yasuda's formula. So now I'd like to show you what the Yasuda's formula is. His formula gives us a condition for when the quotient variety is KRT. So the base field, assume that the base field is algebraic closed field of positive characteristic, and the G is equal to Z of Pz as before. And we take a finite dimensional representation of G. Then, so this is nothing but, this is linear algebra. So we see that this matrix acts on finite dimensional vector space. So we take Jordan decomposition. Then we can find this direct sum decomposition such that each Vi is indecomposable and the dimension is from 1 to p. And we introduce a non-negative integer, dv, which is defined as follows. So for each Vi, we consider dimension times dimension minus 1, which is an even number. So after divided by 2, this is again integer. And we sum up like this. Then this is non-negative integer. Then under mild condition, so the quotient variety is KT if and only if this invariant is at least p. And here, so in the example, so b is equal to L3 over G. So we want to show that this is non-KRT by using this formula. So I'd like to show why this is true. So using this equivalence, we see that dv is now KRT becomes non-KRT, so this is less than p. And now the invariant is 3 times 3 minus 1 over 2. So this is indecomposable. So the invariant is like this. So this number is 3. So if the characteristic is at least 5, then this is not KRT. So this is the reason why P is at least 5. So now I'd like to mention an open problem related to the question D. So let us go back to the question D. So question D is to ask whether the base of morphologized space is KRT or not. So as a reason here, any characteristic, we have counterexamples. So the remaining question is what is the lowest dimensional for which counterexamples exist? So in dimension 4, we have counterexamples, and in dimension 2, it is impossible to hope a counterexample. So only the main case is dimension is equal to 3. And the base, if the base of if the dimension of the base is equal to 0 or 1, then it is clear that B is charity because B is smooth. So only the main case is three-dimensional morphic space from 3/4 to surface. So in this case, the question is open even if the characteristic is very large. So basically in positive characteristic, main equation becomes easy if the characteristic is very large. The only one supporting evidence or some similar some related result is proven by Berlusconi. If the characteristic is at least 7, then B has rational singularities. Charity implies rational, so in characteristic 0. So this looks oh sorry. So at least for surfaces, so in any dimension, charity implies rational. So this is weaker than this one. So anyway, so we have such a result. Okay, now I've finished the details on the 4 questions I have mentioned. So now I'd like to summarize the examples I explained before. So I'd like to so I would like to know the relation between P and dimension. So here I give the dimension of the above example as the examples I explained before. So in the example A, the dimension was 2p plus 1, and the example B, this is 3, and P is 2 and 3. C is also the same. And for the question D, dimension, so if P is 2 or 3, then dimension X is equal to 4. And if P is at least 5, then the total space of the dimension is equal to P plus 3. Then if we look at this list, then it is natural to ask whether counterexample might exist only when the P is sufficiently small, depending on the dimension. So here, I think this might be part, but what I want to say is fixed dimension, then there are only finite remaining P, which gives a counterexample. So I do not have any proof to support this this hope, but I would like to show you some weak evidence supporting this hope. So the first one is about smooth form varieties. So the example we should have in our minds is the one by Totaro. So the example is as follows. So if we take Azure cross field, oh sorry, this is characteristic at least 3. So it is odd characteristic, not 2. Then there exists a smooth fun variety which violates Kodaira vanishing. This is a counterexample to Kodaira vanishing theorem in positive characteristic. And the reason why I show this example is as follows. So the question B and C is related to Kodaira vanishing for smooth varieties because B is asking the vanishing of higher direct image, and C is about the existence of non-trivial torsion line bundle. But for smooth fan varieties, this follows from Kodaira vanishing. So and this example is quite related to question B and C. And there is a conjecture which should be very, very difficult. So BMP conjecture in full general form. So if we take a fixed dimension, then fun variety is bounded. I mean, there exists a flat projective morphism from carry X to S, and both are finite type over Z, such that if K is algebraic closed field and X is smooth fun varieties of dimension n, then this X comes from this family. And usually BAB conjecture is a statement for epsilon KLT case. But today I only consider about smooth case. As a as remarks, so if for the smooth case and over C, I mean, and this is over C, and this is over C, and this is over C, then the result falls from Koramiya Mori. And the epsilon KLT case is studied by Bilker recently. And in positive characteristic, we do not know this holds or not. So this is stronger than positive characteristic case, so this should be very, very hard. But what I want to say is, assume this conjecture, then the counterexample to B and C for smooth form varieties happens only in small characteristic. So this is the next proposition. So assume this conjecture and fixed dimension n, then we can find Pn such that if the characteristic is larger than this Pn, then any smooth form variety of dimension n satisfies Kodaira vanishing. So the proof is easy if we use some results. So if P is large, then this conjecture says that X leads to characteristic 0. So we can use dream illusion or sweet things. I think dream illusion is very famous, and Sweet Smith assures that such X is global figure, and any global figure varieties satisfies Kodaira vanishing. So also Sweet Smith implies this one. Anyways, so if we believe this conjecture, then equation B and C for smooth form varieties should hold for large characteristic case. So to find character example, the characteristics should be very small depending on dimension. As another phenomenon similar to this one, so I mean for only for small characteristic, and take this counter example. So I now want to talk about question C for this setting. So this is total space is 3 and the base space is 1, and the usually called Delphi 5 relations. Anyway, the statement is as follows. We take algebraic closed fields of positive characteristic and take a modifiable space from a Q factorial KT threefold, and the dimension of the base is equal to 1. If the characteristic is at least 7, then any numerical trivial line boundary is actually trivial in a relative sense. Now also we have some results in small characteristic, but what I want to mention here is this one. Okay, so Uh, okay, so I want to give a brief sketch for this first statement. So assume that the characteristic is at least 7, and we take the generic fiber, then we can check that the following two properties is enough. The first property is the existence of rational points for y. And the second property is similar to this one. Y satisfies the similar property to this one. So even if y is smooth and the first part is not so trivial, this is proved by Koryo-Terene. And the second property holds if y is smooth by taking base change to either closed field. For the general case, we need some computation, but we do not give the details. So, so this is a final page of my note. So as a final remark, so this first property is an analog or Graeber high source theorem. So which assures the rational points under some conditions. So in this talk, I talk about modifiable space. So I want to treat the modifiable space. So this is a result in characteristic zero. So if the base field is either closed field of characteristic zero, and we take a Kerr-T variety X, and we take a modifiable space of a curve, then we can find a section. For the smooth case, this holds from Graeber high star, and using the result by Heiko-McConnell, this can be generalized to the singular case. And this is open in positive characteristic. And I now want to summarize the three known cases. So the first, and the dimension is equal to 2, then this is nothing but a tenth theorem. This is a classical result. And the second result, if the geometric generic fiber is smooth and rational chain connected, then this holds. This is result by Doyon star. And the third one is nothing but what I said. The dimension is 3 and p is at least 7, then this is the result I have mentioned before. Okay, so now I want to stop here. Thank you very much.
Thank you. Okay, so let's see if you have any questions. Any questions?
Do you mind if I ask some question?
Yeah, please go ahead.
Sure.
So first of all, I like to ask, so BAB is not known for even for smooth funnel varieties in positive characteristic.
No, no.
I
So
see.
Kolamiya Okamori prove only character zero case.
I see.
Yes, yes. So yeah, even in dimension 3, I think it is open.
I see. Also, I have one more question. So like, if we have like a Mori fiber space, then like, in positive characteristic, I mean fibers, do we know like a rationally connected or like a rationally chain connected or like such something like
So
this?
for if we assume that the total space X is Q factorial, then general fibers are rational chain connected.
I see.
Yes, yes. But I do not know whether special fibers are. So for special fibers, I think in three-dimensional case, it is but 3-dimensional and P is at least 7 or 5, then I think it is true. But the general case is open.
I see. Okay. Thank you.
Thank you.
Any other questions?
So any
Okay, so
update
from-
about the dimension 3, smooth dimension 3, no BAB for?
So I think that it is almost classified, but it is not yet. So it is, I think, in dimension 3 and smooth fan 3/4. I think it's open. So for dimension 3 and smooth fan 3/4, I think it's open.
I see.
Yes, I think so.
Even for P large or something like that.
Even if P is large, I think at least I do not know a reference. I do not know if the proof is easy or not. So, but so maybe the proof might be doable, but I do not know a reference.
Thank you.
Yes, thank you.
Okay, so are there any other questions? If not, then let's thank the speaker. Let's thank the speaker again.
Thank you.
Thank you very much for the great talk.
Thank you very much.
Okay, so I hope well, stay safe, and I hope we'll see you next week or the weeks after.
Yes.
I'll just stop recording now.